In the last lecture, we completed the introduction of Fourier series expansion. I explained what is Fourier series, why we use Fourier series, and what are different types of Fourier series expansion. I told you we use Fourier series for the analysis of periodic signals. So if you have a periodic signal and you want to analyze it, then you can use the tool known as Fourier series expansion. And if you want to analyze the non-periodic signal, then you can use another tool known as Fourier transform. But there are some conditions. You cannot say all periodic signals will have the Fourier series for them, and you also cannot say all non-periodic signals will have the Fourier transform for them. There are some conditions, and as we are having discussions on Fourier series, we will only discuss the conditions for the existence of Fourier series. The conditions for the existence of Fourier transform we will discuss in the next chapter. So let's move to the conditions for the existence of Fourier series. These conditions was given by German mathematician Drichlet. Therefore, these conditions are also known as Drichlet conditions. So let's start our discussion with condition number 1. I will first read the condition and then we will understand it by the help of examples. In case of periodic signals, the number of maxima and minima over the range of time period should be finite. We already know the Fourier series will not exist for non-periodic signals. So the signal here by default is periodic in nature. So periodic signal should have finite number of maxima and minima over the range of time period. The condition is very easy to understand. So let's see one example. Here signal x1t is given and the waveform you can see, and from the waveform we can easily find out the fundamental time period of the signal 0 t0. So this is the fundamental time period of the signal, and in this you can see there is only one maxima. And hence the Fourier series expansion for this signal will exist, because you can clearly see over the range of time period there is only one maxima, and therefore we have finite number of maxima. And you can also check for the minima. For this I will take a different interval of fundamental time period. Here we have t0 over 2, and here the time t is 3 t0 over 2, and this is the fundamental time period of the signal. Now focus on the waveform during this interval and you will find there is only one minima. This one here is the minima. So in case of this signal x1t, over the range of time period we have finite number of maxima and minima. More precisely, we have one maxima and we have one minima in one time period. If you take time period like this, you will have one maxima. If you take time period like this, you will have one minima. Therefore, the Fourier series expansion for this signal will exist. Now we will move to signal x2t, and here you can see the signal is periodic. The same type of structure is repeated after this interval of time, but here you can see there are infinite maximas and infinite minimas, infinite maxima and infinite minima. So in one time period we don't have finite number of maxima and minima. Therefore the Fourier series expansion for signal x2t will not exist. The Fourier series expansion for the signal will not exist. So I hope condition number 1 is clear to you. Now we will move to condition number 2. I will first read the condition. Here the signal is periodic signal. So periodic signal should have finite number of discontinuities over the range of time period. Again we will focus on the time period. Here also we focused on the time period. In this case also we will focus on the time period, and for this signal you can see the time period is this one, the fundamental time period. and in this time period we should have finite number of discontinuities. So let's count the number of discontinuities. Here the value of signal is 0, here the value of signal is 1, here the value of signal is 0, and again the value of signal is 1. So we have one discontinuity here, we have second discontinuity here, and here we have the third discontinuity. We are considering the range from 0 to t0, and from 0 to t0 we have 1, 2 and 3 discontinuities because the value of signal is changing from 0 to 1, 1 to 0 and 0 to 1. So the number of discontinuities are finite, therefore we will have the Fourier series expansion for this signal. Now we will discuss what will happen in case of signal x2t. From the waveform of signal x2t, it is very much clear that the signal is a periodic signal because same type of structure is repeated after a particular interval of time, and this interval of time is the fundamental period of the signal. According to condition number 2, the signal should have finite number of discontinuities over the range of time period. So we will analyze the signal waveform in one time period and we will find whether it is having the finite number of discontinuities or not. I will explain what is happening in the waveform of this signal. Here, this is the width of the first step and this is the height of the first step. Now if you compare the height and width of the second step, you will find the height is half as compared to the previous step, and the width here is also half as compared to the previous step, and the same thing is happening in the coming steps also. So in this way we have infinite discontinuities, and therefore Fourier series expansion of this signal will not exist. In the second example of the first condition, the signal was periodic, the same structure was repeated after t0, but here also we had some problem. The problem was infinite maxima and infinite minima. I will explain what was happening in this case to the waveform. Here this is one cycle. If you see from here to here we have the first cycle, and compared to the first cycle the duration for the second cycle is halved. Let's say tc1 is the duration for the first cycle, then compared to tc1 the duration for the second cycle will be half of tc1. In the same way the duration for the third cycle will be half of tc2 by 2, and in that way we will have infinite number of cycles and therefore we will have infinite number of maxima and minima. So this is all for condition number 1 and condition number 2. Now we will move to condition number 3. Condition number 3 is very important. I will read the condition first. Signal should be absolutely integrable over the range of time period, and this time also we are talking about periodic signal, and we have already had a lot of discussions over the meaning of absolutely integrable. I have explained what do we mean by absolutely integrable in case of energy signals, and we again used it while discussing the stable linear time invariant systems. The meaning of absolutely integrable is very simple. When you integrate the given signal, here in this case we have signal x1t, when you integrate signal x1t, you should get something finite. This means you should get something which is less than infinity. Now there is one thing which may confuse you. We already know for periodic signals there are only two possibilities. The first possibility is that it can be power signal, and the second possibility is that it can be neither energy nor power signal. It can never be an energy signal, and we already know energy signals are absolutely integrable signals. So why we are having this word absolutely integrable associated with the periodic signal in condition number 3? This is because we are talking about the range of time period. We are only talking about the range of time period. But in case of energy signals, we integrated the signal from minus infinity to infinity. In this case, we integrated this signal from minus infinity to infinity, and in that scenario, the result should be finite or less than infinity. But here in this case, we are not integrating from minus infinity to infinity, but we are integrating over the time period t0, because we already know when we integrate the periodic signal from minus infinity to infinity, we will get infinite area. The integration will give you area, and the extension of periodic signal is from minus infinity to infinity. We have already discussed these points a lot of time. The periodic signals will have the same structure repeated from minus infinity to infinity, and when you calculate the area, you will get infinity. Therefore, periodic signals are never energy signals, but when you integrate it in one time period, then the result may or may not be infinity. When it is equal to infinity, we can say that condition number 3 is violated, because the signal is not absolutely integrable over the range of time period. And when it is less than infinity, this means when it is finite, then we can say that condition number 3 is satisfied. Let us try to understand this by the help of two examples. In first example, we have signal x1t, and here when you calculate the integration over one time period from 0 to t0, you will find it is finite. Let's say this value here is a, and the area, which is equal to integration over the time period from 0 to t0 mod x1t dt, will be equal to a multiplied to t0 by 2, because the area is only non-zero from 0 to t0 by 2. So height, which is a, multiplied to the width, which is t0 by 2, you will get the area a t0 by 2, which is finite. Therefore, Fourier series expansion for signal x1t will exist. Very simple. Now we will move to the second example, in which we have x2t, and this x2t is tan t. This is the waveform for the tan function, and we already know when t is equal to pi by 2, the value of signal x2t will approach to infinity. So when you find out the integral over the time period, you will find it is equal to infinity, because when t approaches to pi by 2, the value is reaching to infinity. So obviously the area will also reach to infinity. Therefore, the given signal is not absolutely integrable over the range of time period, and therefore the Fourier series expansion is not possible for this signal. So I hope all the three conditions are clear to you. They are very easy, and if you have already followed the earlier lectures, you will not find any difficulty to understand them. For example, when I explained absolutely integrable, it will not take you seconds to understand what I want to convey if you have already followed the energy signals and stable LTI systems lecture. But still you can understand these things because they are very basic, and if you have any doubt, you may ask in the comment section. I will end this lecture here. See you in the next one.